Let us start the class on date 28 November. My dear students, let's study the things that we have seen yesterday. Let's do a revision. So yesterday we have started studying about the work, and in this part we have studied about the work, various types of work. We have seen that we may have the pressure volume work, we have mechanical work, we have work done by gravity, we have work due to the gravity. We even have the electrical work where the work W is equal to NFE, where E is the electromotive force and N and F collectively are the charges that we understand here. F is known as the Faraday constant. So to understand the work, my dear students, we have taken an example of a cylinder. In this example, we have seen that we have a cylinder. In this cylinder, the gas is filled. So we have gas here. Now we apply some pressure more than the atmospheric pressure, which we call it P external. Due to that, the volume of gas increases. This is what we call it as a compression. So the initial volume of the gas was V1 or V initial VI, which we represented here. You can see here we have drawn a graph of pressure versus volume. On y-axis we have pressure and on x-axis we have volume. And you can see that this is the initial volume. Due to pressure, the volume decreases and it becomes V final. This is your volume of the gas, which is V final. And this area, where this is what it is your delta V, and this is what it is your external pressure PEX, and thus this area by length into breadth, we can write it that area is equal to P external multiplied by delta V. Then my dear students, we have studied that the volume of the cylinder is pi r square h. This pi r square represents the area and this h represents the length of the cylinder. Now pi r square we write area and h is the L, thus the volume change delta L is equal to A multiplied by L, that is our V final minus Vi, but we find uh, but in Vi is greater than Vf, and that is why the value is Vf minus Vi is going to be negative, and thus the volume of change should be negative, and that is why. So you can understand that the volume change, as there is compression, we put negative sign before the volume change because this negative sign represents compression. Then, my dear students, the pressure due to which the volume changes or compression takes place is P external, and we know that pressure is equal to force by area. That is why the force that we apply is pressure multiplied by area, and the here. So work done is equal to force applied multiplied by distance moved. The force applied is equal to pressure multiplied by area, and distance moved is distance moved. When we put this pressure, that is P external, and delta V is your area into distance. That is what we have derived here. That pressure, uh, this is A into L is the volume change. You can see that A into L, that is what we have written as a volume change. Volume change, this volume change minus delta V is equal to Vf minus Vi is equal to A into L. This value we put it here so that we can find out or we can understand that the pressure is P external, uh, the area into distance moved. This is what I'm talking about. Area into distance moved, that is your A multiplied by L, and for A multiplied by L we write minus delta V. So ultimately work done W is equal to minus P external V final minus V initial. This is how we can calculate the work done. But this is what we have done the work in a single step, that when initial pressure was directly converted to the P external, and then at P external the various changes takes place. But now suppose we do the changes into the small steps. So this is what it is, the graph of pressure versus volume when the pressure is suddenly increased from P to P external. Now my dear students, if the same step has been done into the 5 different steps, you can see that these curves P to Q, Q to R, R to S, S to C and A to P are slopy. But now if the same work is done, my dear students, if the same work is done into the many steps, so we can have these many steps. Each step is represented by the black line and the space between them. And if we observe the small portion, we will find that the line become little, the each change is not slopy, but instead of slopy, it becomes straight. Now, the same thing if we do it into the infinite simile steps. So we have infinite steps which we cannot actually count. In that case, each step in the graph shows the straight line. So this slope and this straight line has got some extra area to find, and this is how, if we do the work in infinite simile, very small step at which there is an equilibrium between the system and the surrounding, we can get some extra work. Now, this type of process by which we change the system is known as the reversible change. In the reversible change, we do the change uh, in a infinite simile small step. So the process takes place in infinite simile small step. Each step is infinitely small, and at any instance, the step can be reversed. And the last condition is the process takes place in series of the equilibrium state such that at, at each step, such that the system and surrounding are always in near equilibrium with each other. So this is how, my dear students, we perform the change, and this way when the change is being performed, we can easily understand about the reversible process can be done at constant pressure, constant temperature. Now if we do the same process which is reversible, we do it in constant temperature, that means we do it isothermally. So when we do the isothermal reversible process, my dear students, the work done we get is maximum, because instead of slope, my dear students, now we have got these extra areas, and these extra areas which we get it for our work to be done, these extra areas will will let us to go for more work done. So these areas which I have shown you with the green shaded region are added when we do the change in the isothermal reversible process, and that is why the work done in isothermal reversible process is maximum. So that is what we have proved yesterday. Now, my dear students, we understood the definition of the irreversible processes. So those processes which are not reversible, or processes other than the reversible process, are known as the irreversible processes. Same way, my dear students, we can study about the uh, calculation of the formula for this work. So now let's move more forward and understand the meaning of this integration. W is equal to integration of Vi to Vf. So my dear students, whenever we do the work in infinite simile small step, the the work is expressed in the form of W. So when the work is expressed in the form of W, we write it mathematically in a different form. What we write here is the mathematical representation of work. So when we do the work in isothermal reversible process, my dear students, we write W is equal to integration Vi to Vf minus P external multiplied by dV. These dV are those very small changes that we have done for for the change to the system, and P external is the pressure that we applied, where each state there is an equilibrium between the external pressure and the internal pressure. So if there is an expansion, my dear students, for an expansion we can write P external is equal to P internal minus dP, because the for expansion the internal pressure should be more, but for the compression, my dear students, for compression we can write that P external is equal to P internal plus dP, because the outer pressure has to be applied more, so some extra pressure that has dP that has to be applied to compress the gases. But when we do the process in reversible process or reversible way, there is an equilibrium established between the system and surrounding at each step, and as there is an equilibrium established between the system and the surrounding in the each step, my dear students. For reversible process, we can write P external is equal to P internal plus or minus dV, because there is an equilibrium established between the system and the surrounding. Now, my dear students, we want to calculate the uh, formula to calculate. We want to calculate, or we want to write the derive the formula for calculation of the work done into the isothermal reversible process. So let us move forward and do this, or derive the formula to calculate the work done into the isothermal reversible process. In chemistry, we face problem that can be solved if we relate the work term to internal pressure of the system under the reversible conditions. So, my dear students, we know that for the reversible process, work done is equal to minus V initial to V final, P external into dV. Here we shall discuss about the isothermal reversible process. And in isothermal reversible process, my dear students, we can write that P external is equal to P internal plus or minus dP. So let us put this value, that work is equal to minus integration Vi to Vf, P internal plus or minus dP into dV. Now if we open this bracket, we will get P internal into dV plus or minus dP into dV. But for we know that dP and dV are very small changes. Both these changes, dP and dV, are very small, because we do the process in infinitesimally small steps, and these steps are infinitesimally small, and that is why for both the very small changes, dP into dV, let us say dP into dV is equal to dV. So approximately, let us write dP into dV is equal to dV. So when we write dP into dV is equal to dV, we just write dV, and we have P internal into dV, or we can say that, let us say dP into dV is very small and let it be avoided or let it be neglected. So when we neglect this value, we can have W is equal to P internal into dV. So we can write that the W is equal to minus integration Vi to Vf, P internal into dV. Now P internal is the pressure that we have studied, that we call P internal as a P. So here this P is the pressure exerted by gas on the wall of the container. Pressure exerted. Dear students, can you hear me? बच्चों क्या आप मुझे सुन पा रहे हैं?
Yes, sir.
Very good.
Yes.
Yes, sir.
Thank you. So this P is the pressure exerted by gas on the wall of the container, and that is why instead of P internal now, we just write P, and therefore W is equal to minus V final, V internal to final P dV. My dear students, I have already mentioned this into the previous pages, that we write P is equal to, or here we have P is equal to the pressure, that is the external pressure. That is what we have initially we have derived it, or we have confirmed it. Let me show you once again that here the P that we write is the pressure that is exerted by the gases on the wall of the container. You can easily see it here. Yes, you can see here this tense. Total volume of the gas is Vi and the pressure of the gas inside is P. So from this we have written that the pressure inside the gas is P, and we have put this value of P internal as a P in to derive this equation. So now let's move forward and understand the equation, how we can derive it. So here, my dear students, you can see that we have we have written P internal is equal to P because P represents the pressure exerted by the gas on the wall of the container, and that is what we call it P internal, or the pressure inside the cylinder that is exerted by the gas. Now here, if we take the n moles of ideal gas at constant temperature, we are very well aware that PV is equal to nRT. Remember that I am talking about the ideal gas, and therefore for P we can write P is equal to nRT upon V. Now we have seen that work reversible is equal to integration P into dV for the change of volume in V initial to V final. That is what we have derived, and that is why work reversible is equal to minus integration V initial to V final. Instead of P, my dear students, we just put this value nRT upon V into dV, and therefore W is equal to minus integration Vi into Vi to Vf nRT dV by dV. This dV and V we have written in this form. Now, my dear students, some of the mathematical forms we need to remember and learn. So here I have written that 1 upon x dx is equal to ln x. Same way 1 upon x dx from a to b is equal to into the bracket ln x a to b. This ln x a to b represents the value of x to be put or taken as once the b and then the second time a. So for this we can write, this is the meaning of ln b minus ln a, and for any logarithm, if there is a ln p minus ln q, we can easily write ln p by q. So here ln b minus ln a is written as ln b by a. The same thing we apply here, my dear students, and we can see that uh, we have uh, the value of work reversible is equal to minus nRT, because these are the constants. So we have taken it. Remember that we are doing the process isothermally, so the temperature has been maintained constant, and thus the work initially to work final 1 upon V dV. Now, 1 upon x dx is equal to nlx. So we have written 1 upon v into dv as ln v, and the ranges we have written outside vi to vf. Now instead of v, we can write first vf and then we can write vi. So minus nRT ln vf minus vi, and that is what it goes like ln b minus a is equal to ln b by a, and therefore we can write ln vn minus ln vi is equal to nr ln vf divided by vi. But when we want to convert this ln into the log form, we need to multiply it with 2.303, and that is why in the next step we write 2.303 and log. So this ln is converted into 2.303 log. We have only nRT and log of Vf by Vi. So finally, we can easily understand, my dear students, that the work done in the reversible process, that is W reversible, can be written as 2.303 ln Vi by Vf. Now please remember that if we have log of A by B, we can write log of A minus log of B. When it comes to log of A minus log of B, if we take minus common, then we can write log of B minus log of A, and thus it is minus log of B by A. So if we have log of A by B, we can write minus log of B by A. So log of Vf minus Vi, we can write it as a minus log of Vi minus Vi by Vf, and that is why this minus sign I have removed. So we can have either W reversible is equal to 2.303 minus 2.3 nRT log of Vf by Vi, or we can even write W reversible is equal to 2.03 RT log of VI by VF. Work done in isothermal reversible process is maximum, and it is calculated by this formula, that work done W is equal to minus 2.303 log of uh, VF divided by VI. Now my dear students, if you could not understand anything, you can ask me. बच्चों अगर आपको कुछ समझ में नहीं आया तो आप लोग पूछ सकते हैं. ये पूरी प्रोसेस में अगर आपको कुछ भी ऐसा है जो समझ में नहीं आया तो एक बार पूछ सकते हैं, बिकॉज इट इज एन इम्पॉर्टेंट कॉन्सेप्ट. डू यू अंडरस्टैंड ईच स्टेप? क्या आपको सारे के सारे स्टेप समझ में आ रहे हैं?
सर ये लास्ट इक्वेशन में वी एफ है या वी एक्स है, ये समझ में नहीं आ रहा.
हाँ बेटा, बता देते हैं. आप इसकी बात कर रहे हैं, ये इक्वेशन?
यस सर.
ये वी एफ है ना, यहाँ पे वी एफ है तो वी एफ. ये इक्वेशन और ये इक्वेशन सेम है. दिस टू आर दी सेम. अंडरस्टूड? ये इक्वेशन और ये इक्वेशन सेम है.
यस सर, यस सर.
ओके, समझ में आया?
यस सर.
ओके, और किसी को कोई प्रॉब्लम, कुछ समझ में नहीं आ रहा? डियर स्टूडेंट्स, इज देयर एनीवन हु कुड नॉट अंडरस्टैंड एनीथिंग? Understood? Okay, let's move to the next part. Now my dear students, we are going to understand about the free expansion. Now expansion, that is the increase into the volume. Expansion means increase in volume. Expansion of a graph in vacuum. Now please remember this, that expansion in a gas in vacuum is known as the free expansion. Now what is the vacuum? So vacuum is the condition where there is no pressure. In vacuum there is no pressure of air, and that is why there is no gravity even, and that is why P external should be 0. So expansion of gas in vacuum, that is when P external is equal to 0, is called the free expansion. Now my dear students, as P external is equal to 0, that why P external into delta V or P external into dV, both these terms are going to be 0. That means no work is done during the free expansion of an ideal gas. And thus whether the process is reversible or irreversible, in free expansion no work is done, and that is why we can say that in free expansion P external is equal to 0, that means W is equal to 0. But we know that according to the first law of thermodynamics, change in internal energy is equal to Q plus W. Here the value of W is 0, and that is why in free expansion of the gas, the change in internal energy is equal to heat either absorbed or released. So my dear students, in vacuum, the change in internal energy is equal to the heat either absorbed or released. Please remember this. If process is carried out at constant volume, remember that if the process is carried out at constant volume, change in internal energy is equal to the heat either absorbed or released at constant volume. So this V represents the constancy of the volume. So QV means heat absorbed or released at constant volume, that I've read, heat supplied at constant volume. So when there is free expansion, and even if the volume is even remain constant, then we can say that internal energy is equal, internal energy is the change into the heat of the system. Now my dear students, we want to study about the isothermal free expansion of a gas or isothermal free expansion of an ideal gas. So let's move. For isothermal, T remains constant. Expansion means volume increases of an ideal gas into vacuum. So, and that is into the vacuum. That is why work done W is equal to 0, and that is why P external is equal to 0, because it is the free expansion. There was a scientist, his name was Joule. He also determined experimentally that when Q is equal to 0, therefore change in internal energy is equal to 0. So even the Joule has done the same kind of experiment which we have just discussed about, and he has even proved that when the work done is 0, or when there is when there is a free expansion, the work done W is equal to 0. So if we write the equation delta U is equal to Q plus W for isothermal reversible process. Isothermal means constant temperature, that is delta U is equal to even 0, because change in internal energy is equal to 0. And then, my dear students, if we have the heat exchange, Q is equal to minus W, that is P external Vf by Vi. So my dear students, when we take our delta U is equal to 0, Q is equal to minus W, and when Q is equal to minus W, my dear student, we can say that the heat absorbed is equal to the work done. So Joule, instead of working into the vacuum, he has proved that if we have the work done is 0, or in a isothermal reversible process, if work done is 0, then, or if the total internal energy is 0, because the system is isothermal, and uh, and as it is isothermal, the temperature remains constant. So the heat, or the change into the internal energy even remains constant. And as the change into the internal energy remains constant, my dear students, we can easily understand about change, that delta U is equal to 0, and as delta U is equal to 0, Q is equal to minus W, and the work done P external is equal to Vf minus Vi. आई होप माय डियर स्टूडेंट्स यू अंडरस्टूड एवरीथिंग. बच्चों, क्या आपको सब कुछ समझ में आ गया है? कोई डाउट है तो पूछ सकते हैं.
Yes, sir.
So in today's class, my dear students, we have studied about the formula to calculate um, the work done, or the heat changes into the various process. Now if you move to the next portion, if we think about the isothermal reversible change, isothermal, that is T constant, as temperature remains constant, the change in the internal energy is equal to 0, because internal energy depends upon temperature, and that is why Q plus W is equal to 0, and that is why Q is equal to minus W, and that is what it is equal to nRT ln Vf by V, because minus W, we have seen that W is equal to minus nRT ln Vf by Vi. But if we put minus W, then this sign is going to be plus, and it is nRT ln Vf by Vw, or we can even write that 2.03 log of Vf by Vi. Now suppose we do the adiabatic process. Adiabatic process means Q is equal to 0. When we have Q is equal to 0, delta U is equal to 0 plus 0 plus work adiabatic, and that is why delta U is equal to work adiabatic. Dear students, due to some work today, we have to finish, or stop the class here. I need to go for some work. I hope you have enjoyed the class. If you have anything to ask, you can ask, or you can leave for the next class. बच्चों, अगर आपको कुछ पूछना है तो पूछिए, या नेक्स्ट क्लास के लिए जाइए. कुछ पूछना है? Dear students,
Yes, sir.
do you want to ask anything? बच्चों, क्या आप मुझे सुन पा
No,
रहे हो?
sir. Yes, sir.
तो
Yes,
कुछ
sir.
पूछना है या क्लास खत्म करें?
खत्म कर.
Okay, thank you, dear students. Wish you happy learning.